would really like to thank the Institute and the organizers for inviting me here. This is a great opportunity to catch up with the recent developments in this area, which is going forward right now. I've been working on and off on this topic for more than 30 years, but at some point it looked like it is not as fashionable as it used to be, but now I think it's again very much in fashion, or maybe that's an exaggeration. So I will give a plan for mappings between formal and informal mathematics using grammatical framework grammars and their extensions. So these extensions are maybe the main novelty here, the things that we do in addition to GF. The applications certainly don't give you a human readable output from formal mathematics, human writable input to formal mathematics. So actually we want to have a bridge in both directions. And then maybe use AI generation of formal proofs. I will say just a few words about this. There's a showcase we have thought about. It has to do with the abstract Wikipedia project. So who of you are users of Lean? Oh, wow. And how many are users of Wikipedia? We want to build a bridge there, so we have lots of formally verified mathematical content in Wikipedia and in Lean, and we want to make it available for the languages of the world, starting with 10 languages here, but the actual goal of this abstract Wikipedia project is 300 languages, and most of them don't have much of this content that we want to show, so there's an educational mission here. So that's a showcase that we are kind of having in mind. Related work is all kind of auto-formalization, either using a CNL, controlled natural language, or machine learning, or combinations. A few words about each of those. There is a lot of prior art. I'm certainly missing something here, so I'm mentioning the things that came to my mind that I had been directly inspired by during my work on this. So starting with Lebrun's mathematical vernacular, bridging with his automat system, then Mizar, which is a kind of an informal looking formal language of mathematics. Then maybe a very important milestone for me was this work on Koskoi, Kahn and Terry on extracting text from proofs in Coq. How many of you knows this work? There are not very many, so, but it's yeah, still very inspiring. Then there is the ISAR system, of course, much more natural than ISAR, I would say. There is Fortel, a controlled language for mathematics, and then Naproche, just to mention a few controlled CNL approaches. So I will start with a very short introduction to GF, and maybe as a part of the workshops that I'm proposing, so one could, if anyone is interested, so I could also give a tutorial, but you can decide when, after seeing this presentation. GF, how many of you has used GF? Oh, wow. I'm very surprised. It's a grammatical framework. It's based on a logical framework where you add some grammar rules as forms of judgment. It's based on the idea of separating abstract and concrete syntax. It's actually based on earlier work with another logical framework, ALF. How many of you have used ALF of the 90s? That was my way to, or my road to these topics, actually also to programming in a more serious way. We did this work, some natural language generation to ALF, and then also started with parsing, and then this led to the development of grammatical framework, where these things are put together so that you actually also can have both parsing and generation derived from the same judgments. And then also at Xerox they were mainly interested in other applications than the mathematical ones. Anyway, so this is, you can find it in this web page. Just the simplest example of GF rules. So you have abstract syntax rules saying what categories there are. So categories are basic types, and functions, for instance, disjunction, which takes two propositions into another proposition, and then you have a separate rules for concrete syntax, which say how each category is linearized, to what type it is linearized. That's the lincut rule. So in the simplest possible grammar, we say that the linearization type is a string. So that's like in a context-free grammar. And then the disjunction is linearized by concatenating the linearization of A with the word or with the linearization of B. Okay, no rocket science here. And not even here, if we add some more stuff here, like applying a predicate like even and odd to something, saying that it is even or odd, and an example of an abstract syntax tree and its linearization on the last line here. So the disjunction of x is even, x is odd. From these rules, GF builds reversible mappings from abstract syntax to concrete syntax. That's the linearization directly. It's kind of functional program evaluation. And then parsing is derived by an analysis of the grammar that builds a parser. That's a much more complicated thing, but it's guaranteed by the design of the formalism. The real application of GF is in multilingual grammars, where you have an abstract syntax and then you have any number of concrete syntaxes, and you can do translation from any of those languages by parsing with one and linearizing to the other. Okay? And when you are doing this in a more serious way, you need linearization types of more other than just strings. For instance, in French and in many other languages, you need the parameters of number and gender. So these parameters are language specific. They are in the concrete syntax. So in German you have another type of gender, in Arabic you have another type of number, and so on. Or if your language doesn't have gender, then you don't need to have it in your grammar. So the linearization is really specific into your language. And then you use them to linearize as the values of the linearization functions. So for instance, element, it's like a noun phrase in linguistics. So how many has heard the word noun phrase? I will use it a few times here. So it's a string with a gender and a number. So it could be a feminine plural or masculine singular or any other combination. And then a predicate, here we were using adjectives as predicates. So it is something that depends on the gender and the number to produce a string. And when we apply a predicate in French, so we need to then get the element that we are predicating something about, then a copula, I will show that, so that's the verb to be in any of the different forms it has in French, and then the predicate in the gender and the number of the element. And in this way we get grammatically correct French. But in English this is simpler, so we don't need to mess up the English grammar with these details, and also the abstract syntax remains the same. So in order to help with this, so we can write auxiliary operations, like for instance regular adjectives in French, so that we don't need to write this inflection table all the time, but we use this operation in the concrete syntax or for the copula. And this, and that's, I think, was really a decisive step in the development of usability of GF, is that we started to create a standard library called the Resource Grammar Library, where we collected these, keep collecting these rules, starting with the morphological rules. And here is a rather simple one-slide example of the English noun inflection, where instead of just adding an S, then you might have to change the word in different ways. So you can see the pattern matching here. And if your noun is really not predictable in this way, from typically the suffix of the noun in English, then you can give both of the singular and the plural forms as a backup, or the worst case. So that's the RGL collects these paradigms for the major parts of speech, nouns, adjectives, verbs in 50 languages, or yeah, something like that. What is in some sense even more characteristic is the syntax API. So we have these functions, and here overloaded functions. So everything that is forming a clause, a CL, is called make, MKCL, and you can build a clause from typically a subject and a verb of different kinds and their arguments and so on. And then in the API documentation, you see for each of the cases how it turns out in the different languages. So that's the RGL, and this is not quite the current status, but in the last year, I don't think the RGL has grown very much. So here you have the languages. So the green ones are, in some sense, complete. They implement the whole API, whereas the yellow ones implement parts of it. But they can already be usable for tasks like informalization of mathematics. So the resource grammars are something that are written by someone who is interested and knows linguistics and noun phrases and genders and all of these things. Whereas the applications of GF can use this with very little knowledge about what is inside there. So if we take this simple mathematical example again, so we have the categories proposition, element, and predicate. So we can choose that the propositions are sentences, elements are noun phrases, and predicates are adjectives. And then, we can then implement the disjunction and application of a predicate with combination rules from the syntax API. And both of these two groups can be made language independent, so that we have a so-called a functor, or the functor in the sense of ML programming language, which is parameterized over the resource grammar API. So this is only written once, and then when you add a language to this system, then you have to add the lexical rules for the language. So, and because of these paradigms, smart paradigms in the library, so you can typically give the new lexical rules by just giving the dictionary form, or the form that you find in some glossary, and then apply the paradigm to it, and then you get the grammar instantiated to a new language. There's also a library, not very large, not very comprehensive, but we call it a formal library that has typical formal language things. So, for instance, there is a category of terms with precedence, and it has combination rules for building infix notations or prefix notations with a given precedence, and the lexical rules. So, in the simplest case, you just use the abstract syntax function name, but it can be something else, of course. Here's our first example. So I recently, in order to prepare for this, so I took some interesting material from Wikidata labels. I will come back to that in a moment. And then some part of lean syntax, which I'm still only learning. And I built the grammar. So where you can parse, for instance, an abelian group is a group whose binary operation is commutative. The word binary operation is something that came directly from the Wikipedia labels. And then, so I parse it and then I linearize it to one language, namely Lean, and in the form of a tree bank which shows the abstract syntax. And then I also have a simple unlexer which looks like the code unlexer. So I get this, which is at least it seems to be syntactically correct Lean. I come back to those problems also. So, but of course this language, yeah, so this is the abstract syntax shown in a visual way. It's quite simple in this case. You see these more clearly, the lexical items come from the Wikidata labels. So how many of you know Wikidata? Oh wow. Then I don't need to explain anything about that. So, and of course we have some other languages as well that, and oh, this was, yeah, it was not the same problem. So, so this was, should we push some button here or?
We had this problem for the last days and haven't managed to figure it out.
Michael, do you want me to go to the IT?
Put it on.
Really?
Yeah. Comes back. Well, it does come back, but then it goes.
It usually goes away for like 2 seconds at a time.
I just mentioned getting the guys 37.
Okay, good.
Thanks, IT support.
So this is a quick and dirty grammar using the functor and those languages for which there was enough Wikidata labels for the mathematical concept. So at least for the languages that I know, and I don't know all of these languages, so it seems to be pretty correct, but please point out if that's not the case. Actually, I am tempted to show something here, which is a random generation. But notice that this generation is not type checked, so you get mathematical nonsense, so you could use this as a nonsense article generator. So, yeah, so you could any number of nonsenses. Questions?
So, how do you ensure that the linearization is invertible?
Sorry, how?
How do you ensure that the linearization is invertible?
Yeah, so it belongs to the class of parallel multiple context-free grammars, and there's known algorithms for.
So you check that?
Yeah. So the algorithm is based on the proof that, in some sense, and that this grammar, it's a mildly context-sensitive grammar class, and there's an algorithm that reverts the linearization. It's quite complicated, but it's...
Is it deterministic? There is always just one parse tree?
Under certain conditions. So parse trees, so parsing is not deterministic. There is linearization is under certain conditions deterministic, but parsing is definitely not. And that's, I think, it's an important point because natural languages are are ambiguous syntactically.
Yeah,
And that's also something that I would like to see as a difference from some pure CNL approaches. Anyway, so you could play with this if you want. I will give a link to this also. There are some previous formal/informal projects using GF, and if you I've certainly forgotten some of them, so please complete this with your projects. So the latest one is actually GF Lean in Manchester by Patak Shashank. That was published this year. So now we extend GF, first with the lexical extraction and Wikidata. So we use Wikidata and we use the MathGloss of Lucy Horowitz and Valeria for building mathematical glossaries from text, and they have neatly collected these labels or the identifiers and their for many of them their lean equivalents. So this is a glossary which just has one form of the terms, but then to this we add these smart paradigms where we have inflections of words, and then we add, and there is some novelty here, is that we add heuristic multi-word linearization rules, which we have used in some projects earlier. For instance, there is a rather complete grammar for and informalization of the Z specification language where we used a similar approach. So when you look at the Wikidata, you have these labels, and the concepts typically have more than one word, and depending on the language you have, for instance, in German you might have one very long word, where in French you have 9 words. That's, I think, is the record. And if you want to use them in a grammar or in a text, then you, first of all, you need to form the plural form. And for the plural, you have to know when you put an S or when you put something else in the end. And then you also have to know what the head word of the phrase is. For instance, that in the last one, it's the first word that has to be inflected. And in order to know this, you have to know something about the syntactic structure. Right, so here you can see it in an abbreviated form. And for this we built this heuristic multi-word term, so I'm not going through this in detail now, but it's, and so this shows, for instance, that if the middle word is op, then it's a different thing than that word. So let's, and if none of these heuristics works, which you have to check in some way independently, then you can have a fallback to manually writing the linearization rule by using the kind of the RGL API in a more low-level way. So here is how we have implemented these concepts, and one of them, the plural form of basis, was not, maybe it should be actually predicted. In French, this becomes a bit more complex because you often have to actually inflect several parts of the phrase, and you also have to know the gender. And the second last one is a bit unfortunate because it happens to have the same plural as the singular, but so I can't really show what is happening, but it's okay. So and French is quite a bit more complex superficially, but doesn't need that much more code in order to get a rather good coverage. And then, of course, you always need to have the workaround for the worst case. So that was the first extension. So how we, yes.
How do you deal with articles where the choice of an article might depend on the context established previously in the text?
Sorry?
For the articles in English, for example, sometimes the choice of the article would depend on what has established previously in the text.
Yeah, so this is a part of, it has to be encoded in the syntactic structure. So it's, yeah. And sometimes you can translate the articles as they are, like the definite article in English becomes definite in French, but not always. So this is one of the subtle points. But it's, in principle, I think it's solvable, but it requires some knowledge. Work, yes?
How valuable do you find this for, like, let's say, trying to teach grammar for people who don't, like, how useful would this be if I didn't know French grammar and I wanted to understand how the heck do people, pluralize their adjectives? Can I read this and learn?
So,
or would that not be a suggested item?
So I can tell you a secret if you are a programmer. So the most efficient way to learn a language is to write a GF grammar. And this is true, so many people have done it. But then, of course, there have been approaches and mainly demos, I would say, on, for instance, using GF to produce grammar exercises or auto-documenting the grammar. So,
is there a GF grammar for GF itself?
Yeah, there used to be at least.
Then you can just move it to English.
Yeah, but it's but that grammar is so actually the grammar of GF itself is a context-free grammar, and the GF can read BNF notation, so that's a rather trivial thing. But it's yeah, it's a bit too low level for that kind of nice. But one could always try that. So it's nice to know that there is one. Good. So that was one extension. The other one is core syntax extensions. So, and here we enter semantics, logical semantics. How many of you know Montague semantics? Right? That's the cornerstone of this. How many of you know natural language generation, NLG? Okay, so that's another thing that we are using here. Then again, this is very much inspired by what was first started with Koskoi, Kahn, and Deli with Koch. And then we developed a method of almost compositional functions that is used here. And then we are actually have set a goal of kind of solving the problem that was defined by Mohan Ganesalinam in his monograph, The Language of Mathematics, where he showed the richness of the mathematical language that appears in English textbooks. How many of you know this book? Yeah, so we have a lot of common ground. So we actually, I would like to approach being able to parse all of this language. But we start with something. So first of all, what is compositional? What I showed in the first GF part is compositional controlled natural language approach, where you translate between informal and formal by just parsing and linearization, and the other way around. And here is formally what compositional means. It means that the linearization functions operate on the linearizations of the immediate subtrees. And this requires you to think about it, that you can always have the same abstract syntax for the translation equivalents in different languages. And this is very quick to implement in GF, as I think the examples also demonstrated. It also enjoys from reversibility, so you don't need to have a separate informalization and formalization. Guarantees coverage of lean or some other formalism if you actually have covered it. And easy to trace the translation part by part, because you can align all of the parts of the trees and their linearizations. But it leads to a limited fragment of English or some other natural language, the CNL kind of thing. often unnatural and verbose expressions. That's, I think, how many of you have seen this in the informal generated mathematics? I mean, everything that I've done so far has this problem. Limited usability in parsing natural languages, obviously. So what we can do in GF is that the parsing is incremental, so it helps you write something that can be parsed. But if you want to read a text, then it doesn't really help with that. May generate unwanted ambiguities invisible to the parser if you somehow design your CNL so that something that is really ambiguous in natural language is unambiguous in your grammar. And that's one of the main points in Garnesaling's book, showing that syntactic ambiguity is resolved in more sophisticated ways. And in general, I think it should be rather obvious that different languages cannot be assumed to have exactly the same abstract syntax structure. So to deal with this, so there is this architecture of having a core language plus extensions. And the CNL is some kind of a core language, and it's complete for informalization, but even in that it generates these verbose things, and it's unnatural things, and it's definitely not sufficient for formalization. So here is an example, a very simple example. So you have this proposition. So how would you like to read this in natural language?
All natural numbers are even or odd.
Yeah, or every natural number is even or odd. And what you get via this compositional approach is that the variable is there. The first step of improvement here into an extended language is to factor out the disjunctional predicates, right? And the second one, and that's the more demanding one, is to put this quantifier phrase inside in some argument place. How you do this is that you actually define this extended abstract syntax that allows this, and actually you see this abstract syntax here already, and you give it semantics, compositional semantics, hopefully, but it's not quite necessary, in the core abstract syntax. And then you have the NLG functions, which we want to keep almost compositional, so that which is a nice way to do them. And then we get the extended abstract syntax. So here, for instance, the semantics of disjunctional predicates and of the in situ quantification are shown above, and then the disjunction is formed when you have two atomic enough predications with the same argument. And for this in situ quantification, there's also one condition is that x should occur exactly once in this sentence. Okay, so lots of these things, and we can put them into a pipeline which is quite similar to an optimization pipeline for a programming language by using these almost compositional functions.
Almost compositional?
Yeah, so I think they naturally become almost compositional because they appear in very rare cases. So, and the other cases where you want to propagate it, for instance, a disjunction factoring. So most of the syntactic structures don't have a match at all, so you don't want to define it case by case that nothing happens, but okay, yeah. Yeah, I think to explain it a bit better, but it's that's the method we do it in a kind of type-safe way in Haskell. So robust parsing. there's one idea is to use universal dependencies. How many of you know about this? Or dependency parsing, which can actually be mapped into GF. And we have also used another part of this MathGloss project, the Chicago corpus of undergraduate mathematics, and parsed it and then analyzed and found something. 5 minutes. Yeah, thanks. So
questions.
here is an example of a dependency tree, which we built so that all of the formal parts were just condensed to the word symbol, because otherwise the parser would be quite, that has been trained with some general English, would be quite confused by the symbolic parts. Some of the things, I think I will skip the details of this, but the main thing here is that you can map between GF tree, abstract syntax trees, and these dependency trees in a systematic way. And the common thing between universal dependencies and GF is that you can use the same abstract syntax for different languages, so it's actually a very good step in a pipeline of translation, for instance. The other use we have done is to analyze what kind of syntactic structures there are in mathematics in order to make sure that we have a grammar coverage for all of them. There are quite a few, as you can see, but most of them are very rare, and this is the typical CIF distribution of natural language phenomena. Some other neurosymbolic connections might be that we synthesize a parallel training for neural auto-formalization. Haven't really worked on that, but it's one of the possible things that could be done in slightly different ways. So I will conclude with, I really wanted to, which would be really new to me, to know more about lean, and I hope that you can forgive my ignorance, and help me forward. So I've been discussing with Shashank on his work on auto-formulation with a GF grammar, which was kind of appeared in parallel when I was working on this, so it was quite interesting. So Shashank are you already here? No, but he's coming. We haven't met physically. And there are some functionalities that we had long ago in GF Agda. So I would like to show what these functionalities are, and I would like to have them in Lean. So it's my time off now.
Yeah.
I'm sorry.
We want to have one more question or two, then we should probably wrap up. But this suggests maybe a continuation.
Yeah.
You could
I'm also
be forced.
donating 5 minutes. I'm not in a hurry.
Sorry?
I'm also fine with donating 5 minutes. I'm not in a hurry.
Oh, if you, okay. What does the chair say? Yeah, I will keep it to 2.5. So, I'm very grateful. So in GF Agda, so this is really a 1990s look and feel, but we were able to do this at the time. So this was Agda then, with a graphical interface. Then there was a natural language view without lexical rules. And then you could change the underlying lexical rules, and then you would get to see this. And then you could also parse and linearize Agda code. One problem with Lean, and this actually one of my punchlines is that Lean insists of not having a grammar, but the parser is written by some combinators, which is motivated in a way which is certainly valid, but it makes it a bit harder to work with Lean than to work with Agda, for instance. So I have started learning Lean, like any language that I want to learn, by writing a grammar. So I have a BNF grammar for going through the tutorials and trying to parse everything there with the BNF converter. How many of you know the BNF converter? Yeah, some of you. It's a GF spin-off for programming languages. So the current prototype looks like this, and this I leave for the for the working group. There are good reasons for choosing lean, and this is what I want from the working group. And then we have the big picture of the Informath. So it will not be only lean, I think, but I'm also thinking about whatever dependent type theory based formalism. Thank you very much.